Hello everyone, my name is Gaurang Gupta and today we will be doing another machine learning project which is medical cost prediction. In this we have this insurance.csv file and we have to make a model such that it can predict the charges the insurance company charges based on these parameters: region, smoker, children, BMI, sex and age. So this you can see, let me show you. Here you can see we have continuous values. There are no classes in this. Obviously you can say that these are classes, that we have certain ranges, but again treating this as classes will be wrong. So this is a classic regression problem. Now let's start coding. So first we will import all the necessary libraries. So import numpy as np, import pandas as pd, import os, import cbon as sns, import matplotlib, plotlib.pyplot as plt, from scikit-learn.metrics import mean squared error and mean absolute error. Then from sklearn.linear model import lasso sgd regressor reg and linear regression. From sklearn.svm import svr from sklearn.preprocessing import standard scaler and not and label encoder. From sklearn.ensemble import random forest regressor from sklearn.gaussian import Gaussian process regressor from sklearn.gaussian process.kernels import dot product and white kernel. From sklearn.tree import decision tree regressor decision tree regressor from sklearn.neighbors import neighbors regressor and radius neighbor regressor from sklearn dot model selection import train test split. Now let's import the data. So for importing the data, we will use a variable which is path, which will be an empty string for now. Then for dir name comma underscore comma file names in os.walk /kaggle /input. Then for file name in file names path will be equal to os.path.join dir name comma file name. And then to visualize what we have. Path. Now here you can see I have used a variable at I'm using two for loops here. It can happen that we have multiple files. Here we have only one file, insurance.csv, so we are sure that we will only get one file, but it can happen that we have multiple files. In that case, declare this as a list and then append every path to that list so that you have record of all the paths, because if we have one, two, even I can say 5 to 10 paths, we can copy it, we can deal with that. But when you have multiple paths, it's very difficult to deal with multiple paths. Like in image processing especially, you will have more than 100, 200, even 1000 paths. So it will not be a favorable condition to type or to copy every path. So this is a good approach. Now let's run it to see what we have. So here you can see we have path and the path variable has the path. So now let's make a data frame and get the data into that. So data equal to pd.read csv and then path and then data.head to see first 5 rows of the data. Here you can see we have all the data. We have age, sex, BMI, children, etc. and so all the attributes, and this is the attribute wait a minute, this is the attribute which we have to predict, charges. So now let's move on to data pre-processing. So for data pre-processing we will use a variable lb equal to label encoder, then data sex will be equal to lb dot fit transform data sex, then wait a minute, then data smoker will be equal to lb dot fit transform data smoker, then data region will be equal to lb dot fit transform data region. So here you can see, let me show you. Here we have yes and no in smoker region. So maybe a person is smoker, maybe not. So yes and no. So it will encode them into 0 and 1. Similar with sex, similarly with region. So let's run it and encode them. Now we will have a new data frame test, which will be pd.dataframe data.describe and then test. Now why I did this? Because in this problem we are going to use standard scaler. So when we scale, our output will also be scaled. It will be a scaled version. So our model will also give us the scaled version. It will not give us the actual output. It will give us the scaled output. So we have to transform the scaled output into the actual output. And how we can do that? We can use the standard deviation value. What will happen is that we are using standard scaler, and if you look up the formula of standard scaler, so it is you have to square the scaled value, then you have to add something, and then you have to multiply, I think multiply the difference of minimum and maximum value. You can check it. I'm not going to do it in this video. It is kind of a homework, so do try it. But yes, here you can do it. Now how can you access this? So it will be a simple pandas problem. So let me show you how can you access. For example, we need the standard deviation of BMI. So test BMI and then std, run it. Here you can see we have exact value of BMI's standard deviation. You can also get minimum 25%, so you can get all the values, and these values can be used to change the scaled output to the actual output. So in this you can train the model and on scaled data, but when you are using it as an endpoint you have to scale it back to the normal, because you can't say that the charges are here. You can say the mean charges are 13,270. You can't say that, oh, I scaled this data so now the charges will be, let's say, 0.53, because all our data is in that range, so we have to scale it otherwise. You can't say that because the company will go bankrupt with that. So take care of this factor too. Let me comment this because now we don't need this. Now we will scale our data. So std will be standard scale wait a minute, scalar. Then new data will be equal to pd dot data frame std dot fit transform data. Now I'm using pd dot data frame because whenever you fit through standard scalar, it transforms it into numpy arrays. So we need the pandas data frame to work. That's why I'm using pd dot data frame. And then wait a minute, new data dot head. Let's run both of these, run it and also run it. So here the thing I was talking about, you can't use these values as your final output. These values to train your model, that's okay, but then you have to also de-transform, or you can say reconvert them into the original values. Here we have transformed data. This is not original data. So keep that in mind whenever you are developing a full stack application, that you have to transform your scaled data to the normal data. You can't use just the scale data and say, because here it will predict the value between 0 and 1 because the data is in that, but again, yeah, we have some negative values too, so it will predict like that. Now there is no insurance in the world which will cost you 0.29 rupees or dollars or whatever currency you want to use. So that will be disastrous for the insurance company. So keep that in mind. I'm repeating this because this is a very important point. Most of the people miss it and then they have very weird results. Now let's move on to data visualization. For this, first we will use new data.describe to see the description of data of the new scaled data. So we have the new data.describe. Then we will plot the heat map. So plt.figure fixed size will be 15, 10. You can change it. Then sns.heatmap new data dot core annotations will be true and not equal to true. Then plt dot show. Let's run it. So here you can see we have the heat map, and you can see the attribute number 4 is highly correlated to the sixth attribute. Here the sixth attribute is, let me show you here. Here the sixth attribute is actually our output charges, and the fourth attribute 0, 1, 2, 3, 4, the smoking. So if you are a smoker, it's or not a smoker, it impacts your insurance charges very much. Here even we can see that for a smoker the charges are very high. For non-smokers, again there is some, you can say, age factor also, because if you are of less age you will pay less premium. Again here we can see age is also a deciding factor, not as much as smoking, but yes, it also plays a major role. And here we can also see age, and then I think BMI is also very important in this. 0, yes, BMI is also showing 0.2 correlation value. So you can judge that if you have to remove some attributes, like you can remove this 5, it has very less, or you can say close to none impact on our output, so you can remove it. I'm not removing it. Then we will use sns.pairplot and new data. It will plot the graph between every two attributes, so it takes time. Here we have the pair plot. We have all the attributes, all the pairs plotted. Like the sixth attribute, age, is plotted with the smoker or non-smoker attribute. So here you can get an idea about every attribute or their distribution. So now let's plot the distribution of values for each parameter. For this we will use fig will be equal to plt.figure fig size will be 20, 10. You can change it. Then cnt will be 1. Print new data dot columns dot to list, not to list. Then for call in new data dot columns dot to list, control C, control V. Then plt dot subplot plot no subplot 4 3 cnt. Then sns dot dist plot new data call hist kws will be dict edge color will be k, line width will be 1, color will be blue, and then color will be red. Then cnt plus equal to 1. Then plt dot tight layout, and then plt dot show. So now let's run it. So here you can see, you will see some warnings, but you can ignore them. There is nothing much going on. So this is the part I was talking. So it is showing us the distribution of the data for every parameter. Here the density function. Here you can see the bell curve is becoming. Here two bell curves are there. So you can check that which values you have, or how the values are distributed, how much values of a particular value. Like here you can see you have most many values in this is a perfect example, close to 0, because it is like very evenly distributed and centered towards 0. So you can check it. Now let's move on to training the different models. For this, first we will define our inputs, which will be new data dot drop 6 comma access will be 1. Then output, 1 minute, output will be new data 6. Then x train comma x test comma y train comma y test will be train test split inputs out outputs output test size will be 0.2 and random state will be 0. So let's run it. Now we have our training and testing data. Now we will define two arrays or lists, which will be ms and ma, not na, ma. Ms will store mean squared errors, and ma will store mean absolute errors. So I'm also defining shorthand notation for mean squared and mean absolute error. I'm using just because I don't want to write this mean squared error every time. MAE will be mean absolute error. Run it. Now we will define our function def model training and school. This will be responsible for training our model and getting their errors. So it will take two parameters, model and the model name. Then if name is not equal to best model, then we don't need to train the best model. If you are finding through grid search CV or randomized search CV, if you are not finding through them, then you might need to train. But again, it will be better if you find the best model using grid search or randomized search CV. So model.fit xtrain ytrain, then ypred will be equal to model.predict x test, then mean squared error will be MSC, y test comma y pred, mean absolute error will be MAE, y test y pred. Then we will print the name of the model and its accuracies, mean squared, and also print mean absolute. Then we will append into this name comma mean squared, and in absolute error list name comma mean absolute. Then we will print the new line character, print new line character. Now let's run it. So now we have our training and testing function. Now let's define our array, which will be containing the models and their names. So it will be a 2D array. First will be random forest, and then the model random forest regressor, and n estimators will be 5. You can change it. Then lasso alpha, wait a minute, alpha will be 0.1. Then support vector it will be svr. Then stochastic gradient it will be sgd regressor. Then Gaussian process and we will use Gaussian process regressor. The kernel will be dot product plus white kernel, and then random state will be 0. Then decision tree with decision tree regressor, and k neighbors regressor. Then regression will be alpha will be 1. Then last model will be linear regression, and we'll use linear regression. So run it, and then we will traverse this list for model in models, model training and score, model 1, model 0. So run it, and here we have accuracies, or you can say errors of every model. So it is running. Give it some time. Now it is complete. So here you can see we have errors of linear regression, regression, k-neighbor, decision tree, and all the models. So you can see support vector is most accurate because its error is 0.11 mean squared, and mean absolute error is 0.19. just you can say approximately you can round off to 0.2, but it is still less than all of the models, because some are showing 0.24, some are going to 25, even some are going to 32. So for this case you can say this support vector machine is the best model. Now let's plot these accuracies in a graph so that you can visualize it even more clearly. So now let's plot the accuracies of different models. For this we will use variable bar width will be equal to 0. Not 0 and to 0.2. Then model names will be an empty array. Mean squared will be an empty array, and mean absolute will be an empty array. Then for I in MS, model names dot append I0 and mean squared dot append I1. Then one more loop for I in MA, mean absolute dot append I1. Then fig will be equal to plt dot subplots fig size, and fig size will be 16,8. Then br1 will be np dot arange mean squared. Then plt dot bar br1 mean squared, color will be green, width will be bar width, and label will be mean squared error. Then br2 will be equal to a new list for which x plus bar width for x in br1. Then plt dot bar br2 mean absolute, color will be purple, width will be bar width, label will be mean absolute error. Then plt dot x label will be models with a font size of 16, and plt dot y label will be the loss, font size will be 16. Then plt dot xtext will be r plus bar width for r in range, length of mean absolute, and model names. Then plt dot legend and plt dot show. So run it, and here we have a error. What happened? np dot arange mean squared. Oh, I have to put length of mean squared. Length mean squared. Run it again, and here you have the graph. Here. Now we have plotted mean absolute error and mean squared error. In the graph you can also see support vector machine is showing the least loss, or you can say is most accurate among all the models. So here you can see all the losses are between is less than 1. So I generally prefer to use mean absolute error in that case, because in squaring sometimes it happens that the mean absolute error is more and the mean squared error always becomes less, because we are squaring a quantity which is less than 1. In decision tree it is like violating the rule, but yes, it is better to go with mean absolute error in case you are dealing with errors which are less than 1, between 0 and 1 errors. If you are dealing with errors like 10, 20, 50, 100, it's better to go with mean squared, because then it will be more pronounced, and the effect of the optimization whatever you apply will also be more pronounced, so it will be very easy to see. So for now our project is complete. You can also apply some different things to it. You can apply model optimization, or you can use some different regression models. You can change colors if you want, if you don't like my color style, but okay. So for now our project is complete. Thank you very much for watching the video. If you like this video, please do like, share and subscribe to my channel. And if you have any more suggestions or you want something new to see, do tell me. I will make a video on that too. So thank you very much for watching the video. Thank you.